You know, from the smartphone in your pocket to the jets flying way up in the sky, our modern world is built with just an incredible amount of precision. But have you ever stopped to wonder how we shape materials that are actually stronger than the tools we have to cut them? Well, today, we're diving into the revolutionary shift in manufacturing that's making all of it possible.
So let's start with a really simple but kind of profound question. For centuries, manufacturing was pretty straightforward, right? You take a hard tool and you cut a softer material. Easy. But what happens when that flips? What do you do when the material itself is harder than your tool? What's the move when the thing you need to shape is stronger, or maybe more brittle, or just more complex than any conventional tool can possibly handle?
For pretty much all of human history, machining has been an act of physical force. You're basically just rubbing or shearing a material with something that's harder than it is. I mean, it's how we built everything, from the pyramids all the way to steam engines. But as our materials have gotten way more advanced, this sort of brute force method is really starting to hit its absolute limit.
And this right here is the core of the problem. On one side, you have the reliable old-school method. A tool makes physical contact and literally rips material away, but that creates a ton of heat and stress. On the other side, you have the reality of modern materials. They don't just bend to force anymore. They crack, they melt, or they just shatter into a million pieces. The old ways, they just can't cope.
So, why exactly do we need a new approach? Well, it's not just one single issue. It's more like a giant wall built from four specific, really difficult challenges the traditional methods just can't get over. Let's break them down, one by one. First up, extreme hardness. We're talking about these crazy advanced ceramics and superalloys that get used in things like jet engines and military armor. These materials are so incredibly tough, they would literally destroy a conventional steel or carbide tool that even tried to cut them. Okay, next we've got the complete opposite problem, extreme fragility. I want you to picture those silicon wafers that are used to make computer chips. The absolute slightest mechanical force from a traditional drill would just instantly shatter these super delicate components. No way around it. Third on our list is complexity. I mean, how do you drill a perfectly square hole or a tiny curved cooling channel deep inside a turbine blade? A standard rotating drill bit, well, it only makes round holes. Trying to create these intricate, microscopic, or just plain non-circular shapes is physically impossible with the old toolbox.
And the final challenge is something called surface integrity. See, even when a traditional tool can cut a material, the intense heat and pressure it creates leave behind residual stress and what engineers call a heat-affected zone. You can think of it like a scar on the material at a microscopic level. It weakens the part and makes it way more likely to fail when it's put under pressure.
So if physical force is the problem, what's the solution? Well, the answer is to stop thinking about force and start thinking about energy. And this is the core idea behind non-traditional machining, or NTM for short. It's a breakthrough that overcomes all four of those challenges by completely changing the rules of the game.
So instead of a physical cutting tool, NTM uses focused energy. Now, this energy comes in four main flavors: mechanical erosion, thermal energy that melts or vaporizes material, and even chemical and electrochemical processes that can dissolve material basically atom by atom. The key thing to remember? No physical contact, no brute force.
And this new capability is, well, it's nothing short of incredible. It lets us build things that were once purely theoretical, stuff you'd see in science fiction. But, like any powerful new technology, this new way of manufacturing comes with its own set of awesome advantages and, of course, some pretty significant trade-offs.
Let's start with the good stuff, the benefits. Because there's no direct tool contact, a material's hardness becomes almost totally irrelevant. You can shape hardened steel just as easily as you could soft aluminum. This lack of force also means zero mechanical stress is introduced into the part, which preserves its strength. And the level of precision is just unbelievable, letting us shape features at the micron level, which is absolutely essential for things like advanced surgical tools.
But here's the reality check. This technology is not cheap. The initial investment for one of these machines is really high. It's also generally slower than traditional methods, removing material at a much lower rate. And of course, focusing all that energy requires a massive amount of power. It's a high-tech solution that comes with a high-tech price tag.
So let's wrap this all up by focusing on what's really a fundamental shift in thinking. Non-traditional machining isn't just a better tool. It's a completely new way to remove material. It's all about using precision and finesse over brute strength.
So here's the big conceptual leap. Traditional tools shear material away, kind of like peeling an apple with a knife. Mechanical NTM processes, though, they erode it. I want you to imagine a microscopic, perfectly controlled sandblaster, one that uses high-velocity particles to just chip away material atom by atom without ever physically touching the surface. Pretty cool, right?
And that leaves us with a final thought. We've really moved from an age of cutting with force to an age of shaping with energy. And that's allowing us to create forms and materials we once thought were completely untouchable. So the question is no longer just how we make things, but what we should make. If we can shape literally any material with this incredible level of precision, what impossible things are going to become possible next?